to see better.
Yeah, look at all the ripples on that one.
Yep, I saw them. But we've got better up here.
Yeah. Every time I come here, I see more ripples. Maybe I get ripple sensitive.
Yes.
It's rippled for your pleasure.
That one?
Now these aren't too bad. Ready?
Yes.
Okay, we're now near the summit of Sugarloaf Mountain, and all of the rock around here is the Sugarloaf Formation or Sugarloaf Quartzite, which is a nice, clean, almost 100% quartz sandstone, which has been metamorphosed to a low grade. And this was shallow water stuff. It was shallow water stuff, and it was what the geologists call very mature. That is, any minerals, such as even feldspar, that were at all unstable were broken down. Only the most stable remained. And that, of course, is quartz. It's the only really common mineral that is utterly stable. Give it 1 billion years and it'll go away. But we don't have that much time. This little slab here is one of the best I've seen in the mountain that shows that this was a nice shallow water environment because it has current ripples on here. The water was moving gently in this direction and moving the sand along, which was deposited in little ripples. You've seen these at the beach, where the tide is moving the water in and out. You'll see little ripples in the sand. That's exactly what's going on here. The mountain itself, this is, as I said at the last place, is the core of an anticline, so the oldest rocks are pushed up to the top. And this is even less likely to have fossils than the other one. However, this sandstone here is almost identical to the sandstone that you find just across the valley on the east side of the Blue Ridge, just on the other side of the Frederick Valley. And above that, you find the same sort of calcareous rocks that we saw down below, which actually lies directly above this, in spite of the fact that we've gone up the hill. And those rocks actually contain fossils. So you can put a number on those. And those are basal Paleozoic rocks, Cambrian rocks. These, since they're so similar to the rocks over there, and are also found at the lowest place in the sequence, these are also assumed to be Lower Cambrian. You can make that assumption. Now, is that assumption a good assumption? I remember the geology that I learned when I was going to school in Boston. The Boston Basin is filled with clastic rock, conglomerates, sandstones, and shales, but they never found any fossils in it. They're low-grade metamorphic or not metamorphosed at all. Just to the south, separated by only a couple of miles, is the north end of the Narragansett Basin, which is centered in Narragansett Bay in Rhode Island. Almost exactly the same rocks, conglomerates, sandstones, shales, except that they contain some coal beds with fossils that put a good date on it. And when I was going to school in Boston, they said that the rocks in the Boston Basin were presumably Carboniferous, or same age as the rocks in Rhode Island. Not unreasonable at all. Until it turns out that there are some volcanic rocks in the Boston Basin. And those volcanic rocks contain fossils. No, they contain zircon. And the zircon can be dated radiometrically. And it's 500 plus million years old, which is about 250 million years older than the coal-bearing rocks in Rhode Island. So it's pure coincidence that the rocks in the Boston Basin look almost identical to the rocks in Rhode Island. For that reason, I always take it with a grain of salt when someone says, but these rocks look so similar to the rocks over there. This is separated by a couple of different thrust fault zones. This has moved quite a few miles. This was not nearly as close to those rocks in the Blue Ridge as they are right now when it was laid down. So saying that it's so close and so similar is a little sticky. Now, if you want me to put a better date on it, I can't. As a matter of fact, I will say that I agree that it is probably the same age as those rocks over there on the Blue Ridge. But I am not going to bet the farm on it. It may indeed be. And there is no, short of fossils, there is no good way to get a date on these. Okay, let's continue up to the viewpoint up there, where we'll get to look at some more small-scale geology and a little bit of large-scale. Growing. Okay, we're now standing near the summit, not quite at the summit of Sugarloaf Mountain. All the rocks around here are pure, almost pure quartzite. We'll get a look at it close up down there. There's some nice looks at it. But what I want to show here is the large scale geology. This is the highest point in the Maryland Piedmont right here. Off to our west is the Frederick Valley, which is underlain partly by another Mesozoic fault basin and partly by limestone. The limestone being actually quite a bit younger than this stuff, and it does indeed contain fossils. However, there are faults between here and there, so this wasn't closely associated with those limestones to start with. And how far the faults moved, we don't know. Sometimes you can put a number on it, often you can't, and I've never heard anyone put a number on this one. But it's if I had to make a guess, I'd say it's probably 10-15 miles or so. Then on the far distance is the Blue Ridge. And the Blue Ridge is another major anticline, fairly simple anticline, but very, very large. The far side of it is overturned. That is, it's turned more than 90 degrees, and there is thrusting along here as well. So it was folded, and the fold was pushed up northwestward as well. And on the edges of the anticline is more nice, pure quartz sandstone, which stands up as a very nice ridge. It makes the high mountains over there on each side of the Blue Ridge. Beyond the first ridge here is a mass of greenstone, which used to be a flood basalt, and granite gneiss, that's about 1 billion years old, about 1100 million to be exact when you use the zircon dates. Now we're not going to get to see that on this field trip. One of my alternate field trips starts here and goes west, and you get to see those rocks close up. But I'll tell you about it anyway. That 1.1 billion year old granite is a relic of the assembly of an older supercontinent, not Pangaea, but Rodinia, which was put together by all the continents, or most of the continents, colliding about 1 billion years ago. And the gneiss that you find in the core of the mountains there has been too badly metamorphosed to say exactly what it was, but it's granite in composition. It might have been an intrusive granite, and that's the best bet, but it could also have been rhyolite. It could have been a rhyolite tuff, or it could even have been an arcosic sandstone. But all of the original texture is lost by the high-grade metamorphism that it's gone over. And rock like that is generally found deep within the Earth in a continental collision zone. So that 1.1 billion year rock records the assembly of a supercontinent. Now, how far does it extend? Well, it's found in northern Scandinavia, so it goes that far in that direction. You can find it in central Mexico. I've seen it in northern South America, in Colombia, in the core of the Sierra Nevada de Santa Marta. It's found in much of the Canadian Shield, called Grenville granites. So you find this over a very large area. As a matter of fact, it was interesting when I was in South America to look at the granite gneiss that I found there and think, oh, that's the Baltimore gneiss. Well, the Baltimore gneiss is the same thing up in Baltimore, probably separated in a rift rock and then pushed back together again when the continents came back together again. Anyway, that's the granite gneiss in the center. The overlying, you can see it sitting on it on a particular road cut that we visit, is the Catoctin greenstone. And greenstone is a low-grade meta-basalt. It's a flood basalt that originated from a crack in the ground out of which basalt magma comes and floods thousands of square miles. And this is found in areas that are under tension where the continents are breaking up. The only really good flood basalt, and that was a very small one, that's been seen by people was in, I think, 1734 Laki flow in Iceland, which killed off about a quarter of the population of Iceland. And a series of cracks, I think, totaling about 17 miles long, opened up in southern Iceland, and basalt just came out and flooded the whole area. That's what happens when places pull apart. And that is dated at around 800 million years old, and that dates the breakup of the supercontinent of Rodinia and the opening up of the new ocean of Iapetus, the Iapetus Ocean, which then continued widening for the next couple of 100 million years until things turned around and it started closing again. And then things started to come together to build the new supercontinent, Pangaea. Now, here's a question. Over there on that ridge, you find sandstone very much like this, maybe the same sandstone. As I said, that's under discussion. This sandstone here is standing the highest point in the Maryland Piedmont. In between is the limestone and shale and sandstone valley of Frederick Valley. Why is this the highest point in the Piedmont? Why is this a mountain? There hasn't been any uplift here for a couple of 100 million years. This has been wearing down all that time. And that, of course, is the clue.
It's quartz.
It's quartz. It's A, hardness 7, if you remember. Mohs hardness scale, hardness 7. And B, it's chemically not quite indestructible, but next to it. Whereas feldspar turns to clay. Limestone, calcite, dissolves in acid rain and is hardness 3 besides. So as this area has been wearing down, the most resistant rocks are the ones that end up standing up highest. And that's why this is standing up as a mountain in the Piedmont. If you go down to North and South Carolina, there are knobs east of the Blue Ridge. There's Kings Mountain, for example, which is a high knob in the Piedmont made of quartzite. There's Henry's Knob in South Carolina, from which they get quite a bit of aluminum silicate mined, or they used to. Surprise, it's quartzite. So this is not unusual at all. As a matter of fact, that quartzite down there in the Carolinas may be the same quartzite as this one. Again, that's the best guess, but you don't want to put too much money in that. There are no fossils here and there are no fossils there either. But it's safe enough to say until somebody can prove you wrong. Just don't put too much faith in it. Okay, any questions as to what? Oh, if I were to continue west from here, by the way, on the other side of the Blue Ridge is the Great Valley. Here it's the Hagerstown Valley. Continues down into the Shenandoah Valley in Virginia and up into the Cumberland Valley and Lebanon Valley of Pennsylvania, and then up into the Hudson Valley and Champlain Valley in New York and Vermont. Going the other way, it's going to be the Tennessee Valley, and it's going to be the Coosa Valley in Alabama. It's all underlined by lower Cambrian limestones and dolomites, carbonate rocks, that predate anything interesting happening on this side of the Atlantic, so most of the sediments were all carbonate. But if you look at the sediments in the rock there, overlying the carbonates, you start getting periodically whole bunches of clastic rocks coming in. 3 main pulses of clastic rocks, sandstones, shales, conglomerates. Each of those pulses of clastic rock records a collision and mountain building episode along the coast where something banged into North America. For the first one, it was an island arc that formed off the coast when the ocean started closing. For the second one, it was a Madagascar-type island out in the Iapetus Ocean that banged into New England and the Maritimes. And so in that particular case, the big flood of sediments is mostly up in the northeast, such as the Catskills and the Poconos. And the third one was when Africa, South America, and Europe all banged into North America simultaneously. Africa banged into the Middle Atlantic southward down to Florida. In the Gulf Coast, it was South America that hit it, raising the Ouachitas, for example, and the mountains in West Texas. And from New England north, it was the Madagascar type that banged into it. It's called Acadia, by the way, the land that hit. And it might have been a part that was rifted off Africa earlier, and then hit North America separately, with the rest of Africa following not too far behind. So beyond these mountains here, it's just that series of carbonates and clastics, carbonates and clastics, and carbonates and clastics, 3 sets of each, is all folded into ridges and valleys, anticlines and synclines. And where the clastics are on the surface, you get a ridge, and where the carbonates are on the surface, you get a valley. And so that's these long, long ridges and valleys that extend all the way up the Appalachians from New York State to Alabama. They continue, by the way, down into central Alabama and Mississippi, where they take a right-angle turn to the northwest. You can't see it on the surface because this is all buried by the Gulf coastal stuff. Reappears in Arkansas, goes through southern Arkansas into Oklahoma, disappears into the subsurface again just before it hits the Red River and the Texas line, circles around the central Texas hill country in the subsurface, and reappears in West Texas in the Marathon Basin as the same sort of parallel ridges, disappears again where the new mountains of the eastern Sierra Madre of Mexico hit it, except that in some places in the deep valleys of the Sierra Madre, you can again see the older Appalachian folds, Appalachian rocks, and Appalachian structures reappearing in the cores of those anticlines where the oldest rocks appear. There are traces of it down into central Mexico, but not much at all. In that 200 miles south of the border at Ciudad Victoria in Mexico, there's a nice park there where you can really see those Appalachian structures well for the last time before they're completely destroyed by the later mountain building period of the Sierra Madre Occidental. Where it goes from there, well, there are traces of it perhaps in South America, but they're not, it's really not easy to trace going on there. Too much has happened since then. Okay, I want to take one last look at those rocks down there. There's one little feature I want to show you in those quartzites. Okay, these are beds here of the quartzite, and it's not quite horizontal, but it's not very steeply dipping either. We're right at the crest of the anticline here, right at the crest of the fold. It's steeply dipping on either side, but at the very top, it's almost horizontal. Unless you have, though, a big outcrop, the bedding is almost invisible because these beds are so thick that you can't see them on a hand specimen. So if you had this in the lab, you can't really see the bedding. You have to come out in the field to see it. However, there is also an obscure vertical foliation here. It doesn't show up very well. And there are no sheet silicates in this rock. This is almost pure quartz. It turns out that the pressure was in this direction, and if you put something that is at all soluble, and quartz is slightly soluble in water, where it is compressed, it will tend to dissolve. It becomes higher energy, and the higher energy stuff dissolves preferentially. So you get vertical solution cracks being developed perpendicular to the pressure. It's called pressure solution cleavage, and seldom do you ever really get to see it. Generally, there is some clay minerals present in the rock. It's not a pure sandstone, and of course you get the micas forming then, and you get a very nice cleavage developed due to the micas, And you can't, if there is pressure cleavage, you can't really tell because it's overshadowed by the mica cleavage. Here, since there's no mica, the pressure cleavage, the obscure pressure cleavage, does show up. Now, it's useful in a way because if you've got folded rocks, the pressure is generally perpendicular to the axis of the fold. The fold is generally symmetrical on either side of the axis of the fold. And if the axial plane is, if the fold is asymmetrical, then the axial plane will be tilted. But you can't really see the axial plane in any one place. Yes, you can, because it turns out the axial plane is almost always perpendicular to the cleavage, whether it's a cleavage developed by the sheet silicates or it's a cleavage developed by pressure solution cleavage. So I can tell that the fold here is going to run like here and here, and the axial plane runs in this direction, tilted slightly in this direction, tilted away like this, but not that much. So I can get some large-scale geological structure information by looking at the individual outcrop, which is very convenient at times. Okay, any questions? Can you see? Come up here and look in here and you get an impression of the pressure solution cleavage. It's not obvious. But you can see the rock is tending to break in one direction.